Whenever my family goes out, we often get complete strangers that stare at us. And the reason is because our three sons, they're each a couple years apart, still young. They love to dress alike. I mean, we would try to dress them in different clothes and they'd be like, no, we can't look different because people aren't going to know that we're brothers. So in fact, if you were to look at them, maybe compare them to my husband and I, you might be able to guess that they're our offspring. I mean, we share some similar features. We've got similar birthmarks. We do similar things. But unless you actually had more compelling evidence, maybe if you had a DNA test, you wouldn't really know for certain that we were related, right? You might not be able to tell if they were from our mom and dad distribution. And so visual comparisons of data are only going to get you so far. And this problem of assessing evidence for who or what is truly related, now this is a type of problem that we can solve with statistics. Let's suppose we wanted to test whether two samples are from the same distribution. Now, we could look at their descriptive statistics, like the histogram, the box plot, a bar plot. But again, these visual comparisons alone, they're not going to confirm statistical difference. We need a much more formal method, right? Like DNA testing to tell if these are really my sons. We need a formal method to tell if two samples are actually alike. Now, remember the chicken feed data. We're going to look at this again today. It has the weight and 6 different types of feed that were given to newly hatched chickens. And so, given this data set, we might pose a couple questions about it. First, does the feed for chicken actually affect their growth? And if it does, well, which feed is going to help our chickens grow the largest? Which one is least effective? Now, if feed and weight are independent, okay, meaning neither one really affects the other, then the distributions of our two samples should be the same. Right? So in other words, no matter what feed the chickens eat, their weight should be roughly the same if they were independent. Now, on the other hand, if feed and chicken weight are dependent, then we're going to expect the weight of the chickens to be different depending on which feed they eat. Now, this is the underlying premise of the t-test. How do we determine if two samples are really different from each other? All right, let's go back to that chicken weight data. Remember, we've got newly hatched chickens that are randomly placed in 6 groups, and each group has a different type of feed supplement. Here's how we do that in R. We'd load the datasets library, because that dataset library has the data that we need, the chick weights data, or chick WTS. Call that data forward using data chick weights command. And then let's look at the summary statistics. So summary of chick weights. Now here you see the weights are measured in grams after 6 weeks. And the minimum weight is 108 grams. The maximum is 423 with a mean of 261.3. Now we also see the 6 different feed types along with their corresponding number of chickens in that feed group. So for example, the casein feed has 12 chickens, horse bean feed has 10 chickens, linseed with 12, and so on. Now, let's pull out 2 of our feed groups, and we're going to compare the chickens from those groups. We can do this in R. So let's assign meat to chick weights, where chick weights $feed is equal to meat meal. Basically, that command refers to the row and then followed by a comma and the number 1. So this tells R to look at column 1 to get the values. We're going to do a similar type of command for horse meal. And then notice that I just named these new data sets meat and horse. In fact, if we type those out, we can even have a look at the data values. Now notice our data set is uneven. Meat has 11 entries, horse has only 10. Now, showing box plots for these samples, this is a great way for us to compare them. And here you see the command to do that in R. Now remember, Our goal for this lecture is to determine if two samples are similar, meaning they come from the same underlying distribution, or if they actually come from different distributions, if they're different. Now, your box plot is helping to shine light on your goal. Here we see that the bulk of the chickens in meat meal from the first quartile onward weigh more than all the chickens in horse bean with the horse bean feed supplement. So keep this in mind as we go forward. Now let's look at a plot of the weights by ordered pairs. Right, imagine that we order meat meal from smallest weight to the greatest weight. And likewise, we're going to order horse bean from the smallest weight to the greatest weight. Now take those two ordered sets of data and pair them up and plot them. Now imagine here, if feed had no effect on chicken weight, then we would expect our data points to fall sort of randomly around this red line. This is the line where y equals x. But if feed did have an effect, well, we would expect our points to be shifted either above or below the y equals x line. Notice in our example, all of our points fall below the red line, right? So they're being pulled by the larger values in meat meal. Now, another way to visualize any separation in your data is through a parallel plot. Now, again, we see here that meat meal has several values that are higher than horse bean. And now, there's nothing special about here when I plotted the data on y equals 0 and y equals 1. This was just to separate the two feeds so we could better see it. Now, our graphical data analysis is leading us to believe that there might be a difference in chicken weight due to feed. But in order to draw that conclusion, statistically speaking, well, we can't just look at the descriptive statistics. We have to do a more formal statistical test. And in this case, it's a hypothesis test. Now, the null hypothesis is that the two samples are from the same distribution, and they have the same mean. So the null is that the mean for the meat distribution is equivalent to the mean for the horse distribution. Now, testing whether these two means are equal, this is equivalent to testing whether their difference is equal to 0. And imagine I just sort of moved horse over to the other side, subtracted it from both sides. So now we're testing the difference equal to 0. So this test statistic is now using the difference between the sample means, so x bar of meat minus x bar of horse, and we're actually going to rescale it by the variance to get our sample statistic. Now, a two-sample t-test. This lets us determine whether the means of two independent data samples are different from one another. In a two-sample test, our null hypothesis is that the means of both groups are the same, right? Now, unlike the one-sample t-test, where, remember, we test against a known population parameter, the two-sample test, it only involves those two sample means. Now, you might sometimes see this method referred to as the Welch's t-test because it deals with comparing two samples as opposed to the student's t-test, which is for one sample. Now, we can conduct a two-sample t-test by passing our second data sample into R's t.test function. But first, we can actually verify our test statistic in R. Here you see we've taken the mean and the standard deviation of meat meal and horse bean, and we've calculated our test statistic. So T statistic equals mean.meat minus mean.horse divided by the square root of the sum of their variances. Now, the T statistic value that we get when we do that is 5.059. Now, R is going to do the heavy lifting for you with this t.test function. And so the command t.test of meat and horse is going to return the Welch's two-sample t-test for you. Now, we can confirm that our test statistic value of 5.059, and we have a super low p-value, which leads us to reject the null hypothesis that these two means are equal. Now, the two-sample t-test procedure, it only applies to two samples that are independent, right? And the underlying assumptions of those distributions is that they follow a normal distribution, like in our chicken weight example. But now, what if we wanted to do a hypothesis test on data that's related, okay, on dependent data? So for example, a person's cholesterol level, maybe before and after being on a low-fat diet. Well, in this case, we use a paired t-test. A paired t-test helps us compare two samples where observations from one sample can be paired with the observations from the other sample. Now, we often do a paired t-test when we have before and after measurements on the same subject. We could also do it if, say, we were trying to compare two different treatments where the treatments are given to the same subjects. So for example, suppose I wanted to take body temperature measurements and I wanted to take it with both an oral thermometer and a forehead thermometer on the same person. I'd use a t-test to look at those differences. Now, the paired sample t-test works the same as the one sample t-test, but instead each one sample is correlated to an observation in the second sample. Let's do an example in R. The ice skating data set in the R package called paired data. This gives us the speed measurement in meters per second for 7 ice skating dancers when one leg was either extended, which is extension, or flex, inflexion. Now, this data set is located in the paired data package, so we need to use the install.packages of paired data in order to load that. You could also click on Install Packages in the lower left panel to install it that way. Now, bring the package into our session by typing library paired data. And the data set we want is ice skating. So load it with the data command. And we're actually going to attach it with the attach command. All right, let's have a look at this data set. Now, the first column shows we have 7 subjects in this data set, along with the extended speed measurements in column 2, and then you see the flexed speed measurements in column 3. Now, our summary statistics, this is going to really give us an idea of the spread of the data. And here we see that extension ranges from 1.68 to 2.13. And it has a mean of 1.963 meters per second. Whereas flexion, well, that ranges from 1.55 to 2.1 meters per second with a mean of 1.854. All right, so what's the big question? What we really want to know is there a difference in the speed when the leg is either extended versus when it's flexed? Now, here's a paired plot of our data with extension on the x-axis, and here you see flexion on the y-axis. Now, if there was no difference, we would expect these points to, again, fall along the red line, right, where x equals y. And they're not too far off, right? They fall slightly below the line with a preference toward extension. Now, we could also look at the before and after measurements by subject. Now, here we've sorted the subjects from least to greatest in terms of their average speed. And that's what's along the y-axis. And now we can see that their before and after measurements are plotted with extension in red and flexion in blue. In R, we'd use this command: with ice skating, plot, paired, extension, and flexion, and the type is equal to McNeil. Now, one main assumption for the paired t-test is that the difference of the pairs has to follow a normal distribution. So we've got to check that normality assumption. And actually, our original data, it no longer has to satisfy the normality constraint. Now, we're not directly using those data values in the t-test, we're only using the difference. So we only have 7 points. And look at this histogram. It's not really going to help us see if the data is normal. Let's look at the QQ plot instead. Now here we see a QQ plot of the difference. And notice this looks a lot better. Right? See how our points are falling nicely along the line? And we can confirm this with the Shapiro-Wilk test. That gives us a p-value of 0.6137. So we've definitely got some normal data here. All right, now we're going to walk through some of the details of the paired t-test. All right, here in R, we're going to assign D to the difference in speed between extension and flexion. So notice here in our code, we've called extension, and you see the 7 values associated with it, ranging from 2.13, 1.77, out to 2.08. And also you see our variable for flexion, starting at 1.9, 1.55, out to 2.1. So we're going to take the difference of those two and assign it to the variable D. Now notice we just took them and wrote the difference, and R knew to take a paired difference. So the difference between 2.13 and 1.9 is where we get 0.23, which is our first element of our vector D. Likewise, the difference between 1.77 and 1.55 is where we get 0.22, which is the second element of our vector D. And notice we actually get a negative value. So the last value of D is where we take 2.08, subtract 2.10 to get a minus 0.02. So this difference vector D is the difference between the leg being extended versus the leg being flexed. Now, if there's no difference in speed when the leg is extended versus when it's flexed, then we're going to expect the means of these two groups to be equal, right? So the mean of the extended leg is equal to the mean of the flexed leg. Now, this is the same as testing whether the mean of the difference is equal to 0. So the mean of the extended minus the mean of the flexed is equal to the mean of our difference, D. We're going to test whether D is equal to 0. Now, we can actually quickly verify that in R. Right? We can take the mean of our extended data, subtract the mean of our flexed data, and set it equal to the mean of D, as you see here. So notice the difference of the first means, we get approximately 0.108, which is the same as the mean of our difference D. Now, under our paired test, what's our null hypothesis? Well, here, we need our data, right, to be strong enough to reject that the difference is equal to 0. So under the null hypothesis, we assume that the difference between them is 0, that our populations are actually equivalent, that they come from the same size. So we want our two samples to give us enough evidence that we reject that, right? We want the difference in the means to be far enough apart that they reject the null hypothesis. So our alternative is that we're not equal to 0. Notice here we're testing whether we're either greater than or less than. So it's going to be a two-sided test, a two-tailed test. Now, we don't know the population standard deviation here. And so instead of using a normal distribution, we're going to have to rely on the t-distribution when we calculate our test statistic. The standard error of d bar is going to be calculated as follows. So we're going to take first the standard deviation of d, which is 0.097, and divide by the square root of n. In this case, it's the square root of 7. So when we solve for the standard error, we get approximately 0.0369. Now from here, we can calculate our test statistic, t. And as I mentioned before, we're not able to use the normal distribution because we don't know our population standard deviation. So in this case, our test statistic is equal to d bar minus 0, because this is the mean assumed under the null, divided by the standard deviation of d bar. So that's 0.108 minus 0 divided by 0.0369, which gives us approximately 2.93 as our test statistic for t. Now, we can compare this to our t critical value. This is our value at t alpha over 2, because it's a two-tailed test, with n minus 1 degrees of freedom. And here's the code to actually get that out of R, both for a 95% test, so an alpha equal to 0.05, and also for a 99% test, an alpha of 0.01. In this case, we'd use the absolute value of QT. That means take the quantiles from the t distribution at alpha over 2, so 0.05 over 2, with n minus 1 degrees of freedom, which for us is 7 minus 1. If we wanted to get a critical value for the 99% confidence interval, again, we'd use the absolute value of QT, now 0.01 over 2, with 6 degrees of freedom. So here are the critical values that R gives us. At the 95% confidence level, our critical value is 2.44, and at the 99% of confidence level, our critical value is 3.7. This is what we compare our t-test statistic to. Now notice, at the 95% confidence level, we actually reject the null hypothesis because t is greater than 2.45. And so in this case, we would conclude that there really is a difference in speed when the leg is extended, right, versus when it's flexed. But now look what happens at the 99% confidence level. All of a sudden, we fail to reject the null hypothesis, right? Our t-test statistic is less than 3.71. Now, this is where the p-value's importance is critical, because the p-value tells us exactly where the cutoff is for this particular sample. So in R, we can use the pt function, and this gives us the value of the t-distribution at our calculated test statistic with n-1 degrees of freedom, right? So we've calculated t from our sample, and then we're going to plug that into pt to tell us where it falls along the t-distribution. Now, since this is a two-sided test, we're going to multiply that value by 2 so that we can get an appropriate p-value. Now, we can compare this value to the output that R gives us. Now, notice that our p-value of 0.026 matches the result that we get from R. Here's the code of how we did that in R. We did 2 times 1 minus pt of our critical value, approximately 2.93, with 6 degrees of freedom. All right, let's look at how we do the paired t-test in R. And we're actually going to use the same t.test code that we used before when we did a 1-sample and a 2-sample t-test. But in this case, notice we have t.test of extension and flexion, but now paired is equal to true. So that's telling R that we want to do a paired t-test on these 2 random variables. All right, notice the result that R gives us. It first says, this is a paired t-test. Here's our 2 data sets. And there's our calculated test statistic, t equal to 2.934. And it also shows us the degrees of freedom, equal to 6. And it confirms the p-value that we calculated of 0.02613. The paired t-test also lets you know what the alternative hypothesis is. So in this case, is that the true differences in the mean is not equal to 0. And it also gives you a 95% confidence interval for that difference in means. And lastly, it gives you the sample estimate for the difference. So the mean difference equal to 0.1085. Now, here's a pitfall that lots of my students fall into. They inadvertently do a regular t-test on paired data. No, no, no. In fact, let's see what would happen if we did just that. We did a normal student's t-test on paired data. Do you think it'd give us the same result? Notice here, we've got a p-value of, 0.3046. So in fact, we're no longer able to reject the null hypothesis at any significance level. And the reason for this difference is because our degrees of freedom are lowered for paired data versus independent data. All right, think of it this way. With paired data, we've got 2 values, and it takes these 2 values to provide 1 unit of information, right? Because we're looking at their difference. And so 1 degree of freedom we get from those 2 values. When the data are independent, then each data point gives us a separate degree of freedom. Now here's that test in R. We've done a t-test of extension and flexion, but notice we didn't tell R that this was a paired test. And so it does a student's t-test with our data, but look at our t-critical value. our critical value is 1.07 approximately. And notice how our degrees of freedom jump. And so this is why we end up getting a higher p-value and we're no longer able to reject the null hypothesis. In fact, that 95% confidence interval contains 0, which is our assumption under the null. Now, another pitfall. What if the differences between the pairs are not normal? Don't use a t-test for that because your results aren't going to be valid. In this case, it'd actually be better to use a non-parametric test, like the Wilcoxon signed rank test. This particular one doesn't depend on an underlying assumption of normality of your data. Now, this lecture has given us the tools to differentiate between independent and dependent samples and the appropriate test to use when we're comparing them. But now notice, we're really getting to the point where we're going to actually want to model the relationship between data. And a common way to do that is through linear regression. So linear regression is really going to help us pull out whether there's a relationship between X and Y and also give us a tool to model that relationship.